All right, let's get into chapter 17. It's kind of a total change of what we're talking about, and we'll be talking about electrochemistry. So electrochemistry is the study of the interconversion of electrical and chemical energy. So in other words, a chemical reaction happens, and the chemical reaction involves electron transfer, and we're able to use the electron movement we can use the electrons sort of outside of the reaction to do something else. So it converts chemical energy to electrical energy. And as you can see, electricity is just defined as the presence and flow of electrical charge. In this case, we're going to be talking about electrons mainly as the carrier of that charge. So electrons or ions can carry the charge. We're mostly going to focus on electrons, but we'll see other ions are important too. All right, so we're going to start first with a little bit of a review of Chapter 4. We talked briefly in Chapter 4 about oxidation reduction reactions, and we actually took some very simple oxidation reduction reactions and broke them apart into their half reactions. So we simplified the half reaction, and the main reason you have to do that is because the number of electrons have to be balanced. And so, like we looked at a reaction that looked like it was balanced, but the charges weren't balanced. So in that case, we had to pull it apart, balance out the electrons, and then re-add them together to get the overall reaction. Again, just as a review, an oxidation reduction, or sometimes called redox. So sometimes let me get my little pen going. Let's go with green. Okay, sometimes we call them, an oxidation reduction, or sometimes we'll just call them redox reactions. So a redox reaction always involves a transfer of electrons from one species to another. And the species that loses the electron is the thing being oxidized. And you may remember oil rig as the kind of mnemonic. So the thing being oxidized is losing electrons, and then the thing that is reduced is gaining electrons, oil rig. Another way that we can look at it, and we did talk about this a little bit in Chapter 4, was that if something is oxidized, the oxidation number increases. And if something is reduced, the oxidation number is reduced or decreases. So that's another way of looking at it. It gets confusing sometimes though, remember, because electrons are negative. And so if something's losing electrons, that means it's losing something negative and it's becoming more positive, and that's why the oxidation number increases. If we are gaining electrons, we are adding something that's negative. That means the oxidation number will go down and it's decreased. So just kind of keep that in mind. It's those ridiculous electrons with their negative charge that kind of gets us all confused sometimes. All right, so let's look at an example. In this case, this is kind of a simple equation. The iron metal, we can see that the iron starts with an oxidation number of 0 and it goes up to +2, so the iron is being oxidized. And then the copper is going from a +2 down to a 0, so the copper is being reduced. The oxidation, again, is loss of electrons. Iron has lost 2 electrons to become +2. Copper has gained 2 electrons to go from +2 to 0. Sometimes we use the term oxidizing agent. The oxidizing agent is the thing that oxidizes something else, or in other words, the oxidizing agent is the thing that's being reduced. And by the same token, if you have a reducing agent, that is the species that reduces something else, and so it itself is oxidized. So that can get confusing too. So the thing that is oxidized is called the reducing agent, and the thing that is reduced is called the oxidizing agent, because they do that to the other species. So again, iron is going from a 0 to a +2, so it's losing 2 electrons, so it is oxidation. And so iron is the reducing agent. The copper ion is being reduced because it's gaining 2 electrons, and so it is the oxidizing agent. And just what I was saying before, this reaction is balanced. The way you can tell if it's balanced or not is if the total charges are the same on both sides of the arrow. So in this case, we have a 0 and a +2, so total +2 on the left, and a +2 and a 0 on the right. So it's a total +2 on the left and right. And so because the charges are balanced, then the overall reaction is balanced. That means the electrons are balanced. So we're going to continue on with this, and we're going to actually look at how an oxidation reduction cell is constructed. And if you have, so for example, that reaction that we just looked at, copper and metal, if you do it all in one container, it's a redox reaction. However, you can't really get any electricity out of it. So what you have to do is you have to separate them and connect them with a wire, allowing the electrons to move. So that's kind of what we're going to look at in this chapter. So we have to construct a cell and then physically separate them into the 2 half reactions. And then when the electrons travel from where the compound being oxidized is oxidized, and then the electrons move to the side where the compound is reduced, electricity moves across that. The electrons travel, and it is measured as voltage. So that's where we can get the electrical work out. And so before we do that, we're just going to do a quick review of the oxidation number review so that you can just refresh your memory on that. And then we're also going to refresh our memory on how to balance oxidation reduction reactions. We did the very simple ones in chapter 4, and we're actually going to learn how to balance more complicated ones as well. So let's start with that. All right, so just a few. So here are the oxidation rules. So the first oxidation rule that you should remember is that anything that's an element that's all by itself will equal 0. So the oxidation number of any atom in its elemental form is 0. So if the element's all by itself and its charge is 0, its oxidation number is 0. By the same token, if you have any monoatomic ion, so it's an ion that's all by itself, but it has a charge, it's going to equal that charge. So if you see O -2, then you know that the charge is -2. If you say H plus, then you know the oxidation number is +1. Here it's elemental, so there is no charge. So H2 is 0, O2 is 0. If you just see an element all by itself, or like a metal, nickel without a charge, all of these are 0. If they have a charge, let's go over here. So nickel 2+. If you see nickel ion like that, then you know the oxidation number is +2. A couple of things to keep in mind, even if it's even if they're considered in a compound, anything that's from group 1A and group 2A, even in compounds, will be +1 and +2 because those are the only charges that those ions make. So, for example, NaCl, if Na here, it's in a compound, but we know that it's going to be, Na is always a +1. So all of those group 1A and 2A, like magnesium will always be a +2. So even if it's not a monoatomic written as an ion, even if it's in a compound, there's a mistake there, should be MgCl2. Even if it's in a compound, we can consider group 1A +1 and group 2A +2. Okay, now everything else will be what is in a compound. So of course, oxygen all by itself is 0. Oxygen, if you just see the ion by itself, will be equal to its charge. If oxygen is in a compound, then it's almost always a -2. Now, having said that, there are some exceptions. Every once in a while, if there's a peroxide like H2O2, oxygen will end up being a -1. I'm going to try to just make it simple for you and not give you an exception to the rule, or if it is an exception to the rule, I'll let you know that oxygen is a -1 so that you can use that. But for most cases, if oxygen's in a compound, we can assume the oxidation number is a -2. Okay, so when hydrogen is in a compound, it can only have two possibilities. It could either be a +1 or a -1. So most of the time hydrogen is a +1. Again, that's in a compound. If it's hydrogen element, remember that that's equal to 0. And so if it's in an elemental form, it's still equal to 0. But if it's in a compound where it's a +1, most of the time it's a +1, unless it's paired with a metal, and then it's a -1. So for example, NaH, since Na is a metal, and we already just said that Na is a +1, then H has to be a -1 because it's going to balance. And we'll see that in Rule 6 actually in a minute. But most of the time it's a +1. So unless it's with a metal, it's a +1. Fluorine is always a -1 in all of its compounds. The other halogens will usually be -1 unless there's another element, like for example, if there's another halogen, two different halogens, or if there's a halogen and an oxygen, and then we have to figure out what the halogen is. So it's not always a -1. And then finally, the most important rule is that compounds and ions will equal the total of all the oxidation numbers for a compound is always equal to 0. So it's always equal to its charge. That's probably the easiest way to remember. So for example, if we have H2O, the total of all the oxidation numbers here equals 0. Each hydrogen is a +1, and there's 2 of them, so that's a +2. The oxygen's a -2, so 2 times +1 -2 will give me 0. So they always have to equal 0. If you have a polyatomic ion, the total of all the oxidation numbers has to equal the charge of the ion. So let me just do a few examples for you. Let's do ClO4 negative. So that is a polyatomic ion. So if we look at our rules, like I said, most all the time you can assume, unless I tell you otherwise, that oxygen's a -2. And there's 4 of them. So overall, the charge due to the oxygen is -8. So chlorine has to be, and if you look down here, even though chlorine is a halogen, because it's got oxygen around, we can't assume that chlorine is a -1. We have to figure out what it is. So chlorine has to be whatever oxidation number will make this true, will make the sum of all of these equal -1, because the total is -1. So Cl in this case has to be a +7. Let's do another one. So H2SO3. Again, this one, we have a rule for hydrogen, so each one is a +1. And do keep in mind, oxidation numbers are individual. So if I say, what's the oxidation number of hydrogen in this case? It's a +1. There happens to be 2 of them, so we have to count them both in the total, but the oxidation number of each hydrogen is a +1. We don't have any rules for sulfur, so we're going to have to figure out what sulfur is. And we said that we have each oxygen is a -2. Now this is a neutral compound. Get rid of that so you don't get confused. Overall, the charge is 0, so the sum of all of the oxidation numbers has to equal 0. So this would be 2 -6, and then sulfur has to be whatever will make this 0. So that's a -4 plus sulfur equals 0. So sulfur has to be a +4. So that's how we do it. Of course, like I said, if you've got something like NaCl. Na is a +1, just by nature of it being in a compound, it's always a +1. That means Cl has to be a -1. And Cl, in this case, most of the time halogens are -1 unless there's oxygen or another halogen around. So in this case, that works out. If we have NH3, for example, each hydrogen is a +1. That means in this case, nitrogen has to be a -3 because it has to equal 0. So go back to chapter 4 if you're still having trouble with oxidation numbers. All right, so when we balance redox reactions, like I said, not only do we have to conserve mass, meaning you have to have the same number of atoms on both sides, you also have to make sure that you have the same number of charges on both sides, or technically the same number of electrons on both sides of the reaction. So we have to balance electron gain and loss. The best way to know if that's true is if your charges are equal across an arrow, then across the arrow, then you know you've balanced the electrons as well. So what we did back in chapter 4 is we looked at simple redox reactions, and now we're going to look at some more complex ones that occur in either acidic or basic solutions when there's oxygen and hydrogen around. So when we are balancing redox reactions, what we're going to have to do is we're going to have to pull apart the reactions into half reactions and then stick them back together and balance things as half reactions and then put them back together. So whenever you're looking at a redox reaction, you probably want to look at the skeleton equation, just kind of the general thing that's happening. We want to figure out, well, you may want to figure out ahead of time, but I'll show you if you can't figure out ahead of time, you can still go through the process and you can figure out later which one's being oxidized and which one's being reduced. So you can look at it from two different ways. But we're going to pull out the oxidation half reaction, what's being oxidized, and the reduction half reaction, what's being reduced. And then we also want to know, is the reaction occurring in acid or basic solution? So here's a simple redox reaction. First thing we want to do is figure out what the oxidation numbers are. So zinc, having no charge at all, will be a 0. Hydrogen, it's all by itself. It's got a +1 charge, so it's a +1. This zinc over on the right-hand side is a +2, and the hydrogen that's in the elemental form, which with no charge has to be a 0. So there's our oxidation numbers. So now we can see how what's being oxidized and what's being reduced. Zinc is going from a 0 to +2, so that is oxidation. It's losing electrons. And then hydrogen is going from a +1 to a 0, so that's reduction. So this is a simple case because there's no other elements. And so what we want to do is split the reaction into half reactions to see what's going on. So the zinc is going to zinc ion. So we know that's oxidation. So what does that mean? It means it's losing 2 electrons. 2 electrons are products. If we look at our hydrogen reaction, which is H plus going to H2, is reduction. Now that's not balanced yet, so if we put a 2 in front of the hydrogen, we can see that that's balanced. And now to balance the charges, we have to put, it means each hydrogen is gaining 1 electron, which means we need a total of 2 electrons to balance this equation. So now we can see that we have 2 electrons as products, 2 electrons as reactants, so they will cancel each other out. And so we can add this reaction, we can add this back together, and that makes our balanced oxidation reaction. So like it says up at the top, actually, we could have probably, if we had just looked at the beginning and put a 2 in front of the hydrogen, we could see that it was balanced because we had to have the number of hydrogens balanced. And we know that this is balanced because we have an overall 2+ charge on the left, because it's 2 times +1, so overall the charge on the left-hand side is a +2, and overall on the right-hand side is +2. That means that our electrons are balanced, our charges are balanced, and so this reaction is balanced. Now you may say, well, how can +2 be balanced? Well, there's probably a counter ion that's not being involved into the reaction, maybe chloride or something like that. So it's not important that they be 0, but they just have to be equal to each other. Here's another example, and this one will be a little bit harder to balance, as we'll see, because there's other elements around besides just the copper. If we kind of take a minute first and look and see what's happening, you can see that the oxidation number for copper is 0 because there's no charge. Over here it's a +2, so that means copper is being oxidized. We can keep in mind that since it's going from 0 to +2, that means it has to lose 2 electrons. In this case, we don't know exactly what's being reduced, but we can figure it out. So in this case, oxygen's a -2 because in most compounds it's a -2. Nitrogen has to be such that the total is a -1. And so if each oxygen is a -2, that means it's a -6 overall. So nitrogen has to be a +5. On the right-hand side, hydrogen are usually +1, and so we have 4 of them. And since the overall charge is a +1, that means nitrogen has to be a -3. So nitrogen has been reduced. Notice there's nothing for the oxygen to go to. It'll be in another compound and it'll be a -2. And the hydrogen is, but we'll worry about that in a minute. But in this case, nitrogen is being reduced. And just kind of keep this in mind because it sort of helps you when you're doing these, that you can kind of get a number in your head. In order for nitrogen to go from a +5 to a -3, how many electrons does it have to gain? Well, to get down to 0, it has to gain 5 electrons and then another 3 electrons. So this is actually losing 2 electrons, whereas nitrogen, I think I said that wrong. Nitrogen actually has to go from +5 to -3, it has to gain 8 electrons. So kind of keep that in mind because you'll see that come up later, and it may help you balance these. But if you're still sort of struggling with this, don't be too worried because we can actually, if you go through all the rules that I'm going to show you in a second, you'll actually come up with the same idea, and you should get the same answer. So let's take this, and what we need to do is split them into half reactions. And then we're going to actually add some other compounds to it. And so what you have to know is whether the reaction takes place in an acidic or basic solution. We're going to start with acidic solutions because those are kind of the easiest. So here's kind of the guideline that you should follow for balancing redox reactions. Number 1, like we just did, was to assign oxidation numbers to see what's being oxidized and what's being reduced. And like we just saw, sometimes you can kind of get in your mind how many electrons are going to be transferred. 8 is probably likely because we saw in the last example that it had to gain 8 electrons. The other one had to lose 2, but they're multiples of 8, so probably 8. But if you can't see that, and if you're having trouble with the oxidation numbers to start with, just keep going and follow these rules, and you should be okay. So I'll show you an example in just a minute. So then what you want to do is split the skeletal equation into 2 half reactions. And usually it's pretty obvious. So like in the last example, the copper metal was going to copper ion. It was being oxidized. So the coppers would be 1 half reaction. And then everything that contains the nitrogen would be in the other reaction because the nitrogen is being reduced. And even if you didn't see that, it should be pretty obvious. The copper has to stay together on the reactants and products, and the nitrogen has to stay together so that you kind of have cohesion, consistency, you have the same element. So what we do is split the equation into its 2 half reactions. And then we have to balance those half reactions. The first thing we do is balance any atoms that are not oxygen and hydrogen. Oftentimes you can overlook this step, and it can really mess you up. Just take a glance to see if all the other elements are balanced. Then you're going to balance oxygens, and what you're going to do is add water molecules to the side of equation that needs more oxygen. Because water's around, if you're doing this in a aqueous solution, you've got waters around, so water can be part of the reaction. Then you're probably going to end up with your hydrogens not being balanced. So then what you can do, you may not have hydrogen, but you may. Anyway, then what you should do is add hydrogen ions to the side that needs more hydrogen ions. And so then that will make all the elements balanced. Then finally what you have to do is balance the charges, and the way you're going to do that is by adding electrons, the correct number of electrons, to the more positive side to make the two charges equal. Again, I'm going to show you an example in just a minute. Finally, we're going to combine the two half reactions back together, and to do that we have to make sure that the electrons are the same in the two half reactions. So if they're not the same, you're going to have to multiply each half reaction by a factor so that the electrons are equal to each other, so that they cancel each other out. You can't have electrons in the final reaction. Once you do that, you can add them back together, you cancel out the electrons, and sometimes you might have to cancel out waters or hydrogen ions or something like that. I'll see if I think I have an example. Okay, so let's go back to that last equation. So copper metal reacts with nitrate ion to give us copper ion and ammonium ion. So like I said, first thing you do is split the reaction. Now it says the first thing is to do is oxidize, assign oxidation numbers. Again, if you're having trouble with that, just keep moving on and see what happens. In this case, copper is going to copper 2+, and the NO3 negative is going to NH4 positive. Again, you should be able to see that this is oxidation because the oxidation number is going up, but if you don't see that yet, that's fine. Nitrogen's being reduced. Again, if you don't see that, that's fine. We'll see in a minute what happens when we add the electrons into the half reactions. But like the rules say, the first thing we want to do is make sure everything else is balanced. So we want to balance every element besides oxygen and hydrogen. In this case, my copper is already balanced and my nitrogen's already balanced, so I don't have to worry about those. So now, how do I balance my oxygens? I balance my oxygens by adding H2O to the side that I need more oxygens on. So you can see here on the left-hand side that I have 3 oxygens. So that means I have to add 3 waters because now I have 3 oxygens on the right-hand side. Okay, but now you're probably saying, well, my hydrogens are not balanced. So the next step is to add hydrogens. And the way we do that, and what makes it easy, is we're going to add H+, because of course in acidic solutions we have H+ hanging around. So let's look at this. In this case, I've added 3 H2O, so that means I have a total of 6 hydrogen on this side. I also have 4 more hydrogen on this side, so I have a total of 10 hydrogen on this side. So I need to have 10 hydrogen on the left-hand side, so that's why I added 10 H+. So now every element is balanced. I have 3 oxygens. I have 3 oxygens. I have 6 plus 4, 10 hydrogen, and I have 10 hydrogen. I have 1 nitrogen, 1 copper, and 1 copper. So my next step is, so far so good. The next thing I have to do is balance the charges by adding electrons. So let me erase this so it comes out of the way. Now, what's the best way to do that? Well, the best way to do that is to add up all the charges that you have on one side. So this is the easy one, because on the left-hand side, before I add the electrons, before anything, the total charge of copper on the left-hand side is 0, and the total charge on the right-hand side is +2. So what I want to do is add enough electrons to the more positive side so that the charges are equal. So in this case, that's pretty easy. This is the more positive side. So it's a +2. How many electrons do I have to add to make that total charge on the right-hand side 0? Well, if I have a +2, I have to add 2 electrons. So I have a +2 and a -2, so my total charge on the right is 0, and my total charge on the left is 0. So 2 electrons balances that equation. Hopefully, that should be fairly straightforward. The second equation is a little bit less straightforward, but we do the same thing. So again, before, I've already put that in there, but let's check it out. And if it helps, draw a line here so you know which side is which. On the left-hand side, I have a -1, and there's only one of those, and I have a +10. So overall, this is a +9, correct? +9 total. On the right-hand side, I have a +1 and a 0. So overall, my charge on the right-hand side is +1. So my more positive side is the left. And how many electrons do I have to add to get from a +9 to a +1? I have to add 8 electrons, because -8 + 9 will give me +1. So that's where the 8 came from. And if you were able to do the oxidation numbers that I showed you earlier, those numbers now ring a bell. Oh yeah, I said that the copper was going to lose 2 electrons, and because the oxidation number went up by 2, and we said that the oxidation number came down by 8, and so it kind of makes sense. So you can, if you're doing it, you can kind of double check yourself that you've done it right, because those numbers should kind of ring a bell. So these are my half reactions. Let me erase that so you can kind of go back and see the whole thing. So the fourth step is to balance all the charges by adding enough electrons. So like I said, on the top equation, we had to add 2 electrons to the right to make those balance, and on the second equation, we had to put 8 electrons to the left. And here's just another little tip or a little thing to consider. If you're doing this process and you end up adding electrons to the same side in both equations, you've done something wrong. So electrons, one equation should be losing electrons and one should be gaining electrons. Now they don't have to be the same number yet, but they do have to, when you've got your arrows, we've got to have some on the one equation should have them on the right and the other should have them on the left. It may not be this order, but you should have the 2 equations on opposite sides. So then the next thing we have to do is to multiply each half reaction by some integer so that the total number of electrons are equal. So sometimes, like in this case, they're both even, so that's easy because the least common multiple of 2 and 8 is 8. So this equation we can leave alone. But this equation, in order to get 8 electrons, we're going to have to multiply that by 4. So everything here has to multiply by 4. If we do that, we get 4 coppers, gives us 4 copper ions, and then 8 electrons. So now my electrons are the same. I'm going to go ahead and erase that because that's what's going to show up in a second. All right, so again, we have to multiply that equation by 4, because if we do that, then we have 4 coppers, gives us 4 copper ions plus 8 electrons. And now the 8 electrons, there's 8 electrons on the right-hand side of the equation, 8 on the left, so they will cancel out. And I can add everything else together. And again, keep your arrow in mind. Everything on the left stays on the left, everything on the right stays on the right. So we can add them back together. And like you see, if you want to, you can cross them out here and not even write them. But you can see here we wrote them and then crossed them out either way. So 4 copper metal plus tin hydrogen ion plus 1 nitrate ion. That's on the left-hand side of the arrow. So 4 copper ions plus ammonium ion plus 3 waters. And once you do that, everything, every element should be balanced and the charges should be balanced. So to double check yourself, you can go through everything to the left-hand side of the arrow and you can say, all right, well, here's a plus 10. Here's a negative 1. This is 0. So overall, my charge on the left-hand side is a plus 9. On this side, I have 4 times a positive 2, so I have a positive 8. Here's one more, positive 1. This is plus 0. So we have, again, a positive 9. So as long as they're the same on both sides, then we know that our equation is correct. So let's do one more equation. Here we have iron plus 2 going to iron plus 3. And we have MnO4 negative going to Mn plus 2. So we can pull them into our half reactions, and you can see that I've already figured out the oxidation numbers. Fe2 plus is a plus 2, and it's going to plus 2. So I haven't actually, so we can see plus 2 to plus 3 means it's going up, so it's oxidation. The Mn in this equation, let's go through it. Since each oxygen is a negative 2, and there's 4 of them, Mn has to be whatever will make this whole thing negative 1, so that's why Mn is a plus 7. Here, these are easy because that's a plus 3 and that's a plus 2. So in this case, the oxidation number is going from plus 7 to plus 2, so keep in mind it's coming down by 5, so probably 5 electrons and 1 electron are going to be our numbers. That should sound familiar, but let's just keep going and see what happens. So here we have our 2 half reactions. So the first thing we want to do is balance. Well, first we want to balance all the elements. I didn't put that one in there, but notice that there's 1 Fe, there's 1 Fe on either side, there's 1 Mn and 1 Mn. So those were balanced already. Then we want to balance by adding oxygens to the side that needs it. So because I had 4 oxygen on the left, I added 4 waters on the right. Then I have to add hydrogen ion because now I have hydrogen on the right. So I have 8 hydrogen on the right, and so I have to add 8 hydrogen ions on the left. So I've balanced my H's and my O's. The next thing I want to do is balance my charges. So this one's pretty straightforward because I'm going from a plus 2, sorry, where is it? A plus 2 to plus 3. So it's lost 1 electron because it's only gone up. So a negative 1 will balance those charges. So 1 electron in that case. In this case, I had to have 5 electrons. And we saw that with our oxidation numbers. But again, let's go through this. On the right-hand side, my total charge is plus 2 plus 0. On my left-hand side, I have a plus 8. And a negative 1, so overall that's a plus 7. So what do I have to do? I have to add 5 electrons to make them equal to I always add electrons to the more positive side. In this case, to go from plus 7 to plus 2, I have to add 5 electrons. So that's where the 5 came from. And then the next thing I have to do, let's erase that to make it a little easier to see. The next thing I have to do is balance my number of electrons, and in this case it's pretty easy because the least common multiple of 1 and 5 is 5. So if I multiply this top equation by 5, I get 5s all the way across. Now my electrons can cancel, so I can cancel that out. Everything on the left-hand side stays on the left-hand side, and everything on the right-hand side stays on the right-hand side, and you can see here we can cross off the electrons. You do want to watch out. Now, this didn't work out that way. Every once in a while, depending on what your two equations are, it's possible that you may have waters on both sides. So let's just say it's not that way. But let's say we also had a water on that side, just that it was already balanced. Well, if we've got 4 on one side and 1 on another, we can cross 1 off both sides and balance them out, just like algebra. So we can sometimes simplify the equation one more time if we have to cancel everything out. But of course, in this case, we didn't have that, so I don't want to confuse you. But if there happen to be waters on both sides, you could cancel out. If they're both the same, obviously you can cancel them all out, or you can subtract from both sides to get the correct number on one side. And same thing with H pluses. If you have H pluses on both sides, you can subtract some so you can get rid of them on one side. I may have an example coming up in a minute. So there's the balanced equation. We'll erase that to make it look nicer. There we go. So you can erase out the electrons. All right, so that was balancing the redox reactions. Acidic solution, which if you can get that, that's probably mostly what I'm going to be focusing on. But what if we actually happened to have a basic solution instead? Well, remember, every time we have a hydrogen ion, if it happens to be in a basic solution, so if we have an OH negative around, they're going to combine to make water. And so if you happen to have hydrogen ions around and your solution happens to be basic, you have to do one more step to make sure that you have no hydrogen ion around. So what you're going to do, once you've balanced to where we got to an acidic solution, you need to figure out how many hydrogen ions you have present, add the same number of OH negative ions to both sides, because remember, everything's already balanced. So we have to add OH negatives to both sides because the H pluses can't exist, so they're going to react with OH negatives. So now, but to keep everything balanced, we have to have the same number of OHs on both sides. And then for every H plus and OH you have, you're going to get a water. And then finally, you may have to cancel out some waters. So let's do an example of that. I think we're going to start all the way at the beginning for this one. Again, so you can get one more example. So the first thing we do, balance this in a basic solution. Well, do everything we just learned for an acidic solution. So use with the acid rules. Break the equations into 2 half reactions. Then you're going to balance everything except the oxygen and hydrogen. So that's what I did too. Balance everything else except O and H. So I had to put a 2 in front of the bromine. Oh, and actually a 2 in front of the chlorine. Now the next thing you want to do is balance the oxygen. And so in this case, because I have 2 oxygens on the left, I need 2 on the right, so I added 2 waters. Now my hydrogens are unbalanced, so I have to add 4 hydrogen to the left. The next thing I want to do is balance my electrons. So over on the left hand, on this top reaction, I have a -2 plus 4. So overall, it's a +2 charge. Overall on the right is 0. So I have to add enough electrons to get these 2 charges to be equal. So I'm going to have to add 2 electrons. On this side, I have a -2 and a 0. So again, it's the more positive side. Even though you don't have a positive side, it's still the more positive side. In this case, 0 is more positive than -2. So we have to add 2 electrons to the right-hand side to balance that. So in this case, it's nice because they're both 2 electrons. So we actually don't have to worry about balancing the electrons. So that you can skip that step. So in this case, my electrons are balanced. But we want to do one more thing. Well, we can either add them together now, or we can add the hydroxide. So let's see what's coming up next. So we went ahead, added everything together. Like I said, the electrons are the same, so those will cancel out. And if the question said to balance in an acidic solution, you would be done. That would be the answer. But because it's in basic solution, we have to get rid of any H pluses. So what the rule said is to add as many OHs to the side with and you know, if you needed to, if you had H pluses on both sides or H2Os on both sides, you could cancel those out first. So again, make sure everything, you want to simplify it as much as possible. But in this case, because I have 4 H pluses on the left, I have to add 4 OH negative on the left. So I'll do that. Well, if I add them to the left, because right now everything's balanced, if I only add them to the left, it will throw me off balance. So I'm going to also add them to the right. But what's going to happen here is that these 4 H pluses and 4 OHs will become 4 waters. So notice that the 4 H plus and the 4 OH negative become 4 waters. This just continues. This side, nothing happens, but we do have the 4 OH negative. So now this looks like it's balanced, and it mostly is, but keep in mind that I have 4 OHs, 4 H2Os on that side and 2 on that side. So what I can do is I can subtract 2 from both sides. So if I subtract 2 from this side, I have that cancels that out. And if I subtract 2 from this side, I'll have 2 left over. So let me erase that so you can see when I pull this up. So again, we're just going to subtract 2 H2Os from both sides. If you subtract 2 from the right, they cancel out. If you subtract 2 from the left, you'll have 2 left over. And so now that's my balance equation. And since we have a basic solution, the OH negatives are fine. So that's an example in basic solution.